polylog canonical differential equation in intersection theory.
Yes, so thank you for the invitation. It's a pleasure to speak here in these flavors of amplitude seminar. So I hope today I will try to convey you two more or less flavors. So what is a canonical differential equation and how intersection theory can help in Feynman integrals. So if these words don't make sense to you now, I hope that they will at least a bit at the end of this talk. And it is based on these two papers in collaboration with some people both in Bonn and both outside. Okay, and I will do this going through the geometries that you will see that appear in Feynman integral and in amplitude in general. So then, having said that, well, since this is the flavors of amplitude, we have to start from saying something about particle physics. So we know, for example, that now, okay, we have the LHC, that's probably the biggest experiment, one of the biggest experiments that we have. And this will still give us data for the next 2 decades, more or less. We still have the phase of high Lumi LHC that will still give us a lot of data. And we have a lot of parameters that we still want to measure more precisely. And for example, some of them are concerning the X sector that we still don't know much about. So the LHC will really ask for precision now in experimental, for example, in this experiment. On the other hand, we also now have access to gravitational wave precision experiment. Indeed, from 2015, now we know we can actually measure gravitational waves. And we have many experiments that do so. So, for example, LIGO, Virgo, Cagra, and some upcoming one like Einstein Telescope, Cosmic Explorer, and LISA. And again, here as well, we can use the gravitational waves as a tool for having higher precision. And for testing gravitation, for testing Einstein gravity, black hole and neutron star properties, and also for finding possibly new physics as well here. So we can see that both from these two perspectives, experiments are giving us precise data, and so then we as a theorist, we need to also have a precise theoretical prediction. Now, you can see here, this is a depiction of proton-proton collision. It's not too simple. So we have the protons incoming, we have the arc part of the scattering where we have the gluons and the quarks and so on. Then we have the parton shower, and then we have the hadronization. So it's really a multiple step process. On the other hand here as well, we have first the in-spiral phase, and then we have the merger, and then we have the ring down. So not all of these can be treated with the same formalism. So for example, here in the merger, we need strong gravity, or here, for example, we need also the chiral perturbation theory. We need to understand the hadrons. But for example, the hard part of the scattering and the in-spiral phase here can actually be dealt with perturbation theory. And so then this gives us access to QFT-like tools that we can actually use to give some theoretical predictions. And so then this brings me to one of the most important objects in QFT, that is the amplitude. And we know, for example, that the amplitude is analytic apart from its singularities. Indeed, also unitarity tells us that the amplitude, if we have production of particles, the amplitude has to have singularities. What kind of singularities do we have? We have poles when a single particle state go on shell. And so then by this, I am cutting the propagator. This means that this particle is going on shell. But we also have something else, so branch cut, when multiple particle states go on shell. And in this case, the singularity, so the discontinuity that then the amplitude has as a, let's say, worse singularity, so square root or also logarithms. And so then here I want to say that the singularities are really important from a QFT point of view, because they really tell us, for example, the particle content of the theory. And the amplitude is heavily constrained considering the singularity. On the other hand, we compute the amplitude. And in modern times, the way we do to compute amplitude is to first we remove all the tensor structures, so everything that comes from gamma functions, polarization, we remove it away, so that we are left with the computation of families of scalar Feynman integrals. And so then here is where a lot of effort of the community is put on. Now, we have decades of calculations that have shown us that for processes at one loop, we can always package the amplitude in this form. Now, here we have an algebraic function that depends on the kinematic. So this S will be the kinematic variable and X will be my integration variable throughout the talk. And then here we have an integral, actually a chain of d-log integration. By d-log, I really mean something that is a simple pole. So like here would be 1 over f, derivative of f times dx. So really like a simple pole instead with a d-log form. And so this is the transcendental part of the amplitude. And what is this? What does this mean? Well, this carries the information coming from the singularities. So you can really see that if you manage to have a form of the amplitude in this way, your singularity structure is manifest because it's really packaged in this integration. And this also is what we expect from locality, because from locality of interaction, we expect that the poles happen like we have simple poles in the particle production. So this seems a natural form in which we want to have our amplitude expressed in terms of. And this has been, it's a form that has been evident since now some years, and it's called, these integrals are called pure, because they are only given by logarithmic powers. And so then one of the questions we might have is, what stays beyond? So when we go beyond one loop, what happens, why it's not always possible? And that's what I will tell you today. First of all, let me recap. When do we actually see these polylogs? So if now I'm trying to compute the discontinuities of my amplitude, so I am trying to compute all the discontinuities that I have, and while doing so, I only get at most rational function, well, then this means that my integrand lives in the complexified momentum space, and we can have at most some singular points, because then if we have something worse than a singular point, like a branch cut, we cannot get rational function if we compute a discontinuity. So then this means that my integrand lives really in this place. And what are the differential forms that span this space? Well, they are only of this type. So all the other forms are dependent on these forms. So we really have simple poles that span the cohomology of the Riemann sphere. And so then in this case, it makes sense that we can actually find an integral that really looks like a chain of the log integration. And it turns out that the part that depends on the dimensional regularization parameter, because our amplitudes diverge, so we need to regularize them. And so epsilon will always appear in our calculation. But it turns out that if you can actually find a form in which the epsilon part more or less decouples from the geometric part that depends on the space we're integrating on. And so this is the pure integral that we saw before. By the way, if you have questions, feel free to interrupt. And but this is not just pure, it's actually canonical. And what does it mean to be canonical? It means that it satisfies some particular differential equation. So first of all, let me say that a family of Feynman integral is a basis. We will see it later why it's a basis. For now, you have to believe me. And so then you can actually compute differential equation. So you can add with the external kinematic and compute and get a matrix that multiplies again your basis of integrals. And a priori, this can be general, so can depend both in S, our kinematics invariant, and also in epsilon. But you see, if you have this special form, epsilon more or less factors out, and so you can always put it in front in this case. Otherwise, it's not for granted. Then, moreover, you can see that the entries of this matrix have to have simple poles. Indeed, if you now act with a derivative, you will just get a d-log outside. And so then your matrix here will only have simple poles. And maybe this is not evident from here, but the differential forms will also be independent. So this means that if you take any linear combination of these d-log forms, even up to total derivative, so they are not just zero, but they also can never give a total derivative. And so this is what it has been called canonical. Why is it a good property? Well, because, for example, you can take the first line, and now you can formally solve it. And so it will give you a path-ordered exponential. And okay, so you might think, okay, path-ordered exponential, I don't do much with it, but since we are not really interested in any value of epsilon, but we're interested in a Laurent expansion because we want to expand in any order in epsilon, then what we just want is to have, we can just series expand this object. And so then here you will see that you will get powers of epsilon that then multiply iterated integrals. And these iterated integrals have a special form, because since in B we only have simple poles, then a chain of integration over the simple pole will only give logarithms. And also, can I remove this? Or maybe not. No, okay, it's not too important. No. Okay, it's not too important. I just have one. Okay. And they also have another property. They have the same transcendentality. Well, this means that if you now expand, for example, at the first order, you will get epsilon. And then since it's the first order here, you will just get a log. And then if you continue expanding, you will get an epsilon squared. And since now it's an iterated integral, you will get a log squared. So every power of epsilon is also multiplied by the same power of logarithmic divergence. Okay. And why is this good? So not only if we find this form, we can actually solve the integral, but if you don't want to solve the integral and you want to try to bootstrap it, you can use this property to understand what kind of function you are expecting. So if you know that your solution will only have logs, well, then you only use logs to bootstrap your solution. And moreover, if you know that you have to have a uniform transcendentality, you also know that at any order in epsilon, you have a specific power of logs. So knowing that you can have something like this can help both in solving it, but also in actually bootstrapping it. Okay, so I hope I tried to convince you why this is a good form. And now,
bootstrapping here means making an ansatz?
Yes, you make an ansatz of your integral, and then you use this, you can use this. Yes. Okay, but what goes wrong then? Well, so this, it's true when we have the simplest geometry, but that's not always the case. So if you now evaluate your discontinuities and you get something that's more than rational, because for example, you have a branch cut, you can get transcendental function. But so then if you have transcendental function, it means that your space is not just the Riemann sphere with some points removed, but it has to be something more complicated. And the simplest generalization that we can have is the torus, because you can imagine like you have two branch cuts and then two copies and you glue them and you get a torus. And so now the question is, what forms do they live in the torus? Well, we can still have something similar to before, so something that has a simple pole, but this time it's not really just the simple pole, it also contains the square root of the elliptic curve that is isomorphic to the torus. But okay, still this is not that bad because we still have a simple pole here. But however, if you now look at the geometry of the torus, you know that this cannot be all of it. Because for example, you can have this cycle that goes in this way, and you can also have this cycle that goes in the other way. And you know that these two cycles are independent, and so they also correspond to two differential forms in the homology that are not like not this one, but they are indeed this. So the x over y that, as you can see, doesn't have any pole, and this other form that's a combination of x squared and x that has a double pole and doesn't have residue. And so here you really see a difference with respect to before. We don't have only simple poles, but we have something that's a bit more complicated than that. And so then one question that we can ask is that, can we keep similar properties as before? Can we still get this simple pole structure that we would expect? And I will try to show you that we can. And I also can already tell you that this works for all the geometries that we have encountered so far. So far in Feynman integrals, also higher genus curves have appeared, also Calabi manifold have appeared, also in gravitational waves. So, but this so far works for everything that we have encountered. Okay, so I will try to show you everything with this example. And so this is the usual, maybe for me at this point, sunrise integral. So it's the maybe next to complex two-loop integrals corresponding to the bubble. And here we have these two propagators that have mass small m, and this propagator that has mass big M. So this is the usual way of writing the integral. So here we have one denominator 2, and denominator 3. However, as I told you before, to make this integral form actually a basis, we need to add these other two propagators that are called irreducible scalar products. They won't really play a big role. I just want to say that they are here to actually be able to write the differential equation. Otherwise, we couldn't. And okay, this is the D from the dimensional regularization parameter. And so then, why is this a good example? Because we can split it into two cases. So if we put capital M to 0, we will get a polylogarithm. We will get polylogarithms in the end. If we don't, we will see elliptics. And so then I will show you how you can actually see it. And so then maybe the question that we want to answer is, can we actually find these integrals that we said before that can collect all the singularity structure? And are these properties independent on the geometry? So we will see a difference between elliptics or not. Okay, then having said that, I need to do a bit of analysis of the integral to show you what you actually get. So let me start. And before, I just showed you the normal loop momentum representation. So we have our integrals in terms of loop momentum. But to see this geometry appearing, it's actually better to go to another representation. And it's usually all parametric representation work. Now I'm choosing specific one that is called Bykov. And you can see it here. Instead of having denominator 1, denominator 2, denominator 3, I have 3 new variables. So I'm changing variable, and each of these variable is one of the previous denominator. Indeed, now I have 5 integration variable here. And this is the change of the Bykov polynomial that it comes from the change of variable. Okay. So now still, this looks still a bit complicated, so we can do something to simplify. So first of all, we can fix the number of dimension. And so here, okay, you can more or less see from here that 2 is a good number, but it's also a good number because you have only 2 legs. But okay, this maybe you have to trust me. D equals 2 is a good dimension where to evaluate the integral to, but we can always shift to D equals 4. Okay, if we do that, it simplifies a bit, but still we have 5 integration variable. And so now what we can do is a bit the contour and choosing it such that we encircle all these poles, so that this will give us simple residues. And so indeed, this is called maximal cut, because this is equivalent as if we are cutting all the propagator, we are putting all the particle on shell doing this process. And this simplifies a lot the structure, because then now here dx1, dx2, and dx3 go away. They just give us a residue. And so we are left with a dx4 and a dx5. And now you can actually see that the dx4 is not that bad. It's actually the product of 2 simple poles. And this is also what we wanted. So we wanted to find an integral that has simple poles. And indeed, now we can actually write it as a derivative of a logarithm. And if we do so, then we will get the first part, so the derivative of the logarithm that we wanted. But from one of these 2 residues, the one that we are not integrating over, one of these 2 poles, the one that we are not integrating over, we will get a residue that will then affect the other part of the integration. And if you see here, this is a quartic polynomial in x5. And so it's the equation that defines you an elliptic curve, because the roots are not degenerate. So then this is an example on how you can see the geometry connected to an integral.
By the way, here you have 2 equal masses among the 3 masses.
Yes.
What happens when I have 3 masses?
You will still get an elliptic curve, but it will just be a bit more complicated. So the roots will depend on both the masses, but the geometry stays the same. Yes.
Can I also ask, when you were saying you could easily shift to 4 dimensions, do you mean that you have some differential operator that you can...
Yeah, they are called dimensional shift relations. I'm not sure if it's a differential operator, but you have some function that then if you multiply 2 gives you the 4-dimension one. Probably yes, they are actually derivatives, because as you see here, the dimension appears still at the exponent, so it's not that different from like one of these new 5s. So probably it's something like that, yes. Okay, so then let's start with our first case, so the m equals 0 case. What happened? Now 2 of the roots that we had before collide, and so then here they give us a simple pole, and we're left with the square root of a degree 2 polynomial. Okay, so then let's look at our differential form. Let's start by putting nu 5 equal to 0. So if we do so, then we have a pole in x5 and a square root in also in x5. And so we have these two contours, if we want to understand this integral here, this part here. And now, however, they are not independent because we have the global theorem of residues that tells us that they are related by a sign. And so then if we want to compute this integral, in the end, we can do it both around C1 and both around C2. And for example, if we do it around C1, then this gives this just gives us a residue in x5 equals 0, and we get a square root. What does this mean then? That again, our integral also here has a simple pole. So again, we can write it as a g log, but it's not a pure simple pole because we have still like some algebraic part. And so our integral will behave like something 1 over this square root and then times a d log. And this is called the leading singularity. But so then if we want our integral to only be a product of d logs, we can just multiply it by this leading singularity. And so in this way, we found an integral that behaves like a chain of logarithmic integration. That is what we wanted to find. Now, you can check, and if you put nu 5 equal to -1, and I will actually use, you will see it now, this is an independent integral. Why you see it? Because if you put nu 5 equals to -1, then this becomes x5, so you can, these two cancel out. And so the pole in 0 disappear, but then you get a pole at infinity. And so then this gives you an independent differential form. But again, you can do the same analysis again for the theorem of residue, and this time you even get a 1, so you don't get anything too bad. And so this integral with a -1, it's already a good candidate for an integral that's a chain of d logs. And so we found another candidate. Now you can check and you put nu 5 equals to any other value, and the differential form that you will get are dependent on these two. And so this is really our basis of integrals. And in this case, we actually indeed managed to do what we wanted to do at the beginning, so to really have the singularity structure manifest. Okay.
Can you guess the priori how many of this J you have?
Yes, yes. So there are other ways to do that. Okay, now, okay, this, sorry. Yes.
So for generic, for nu 5 different from 0 and -1,
yes.
In general, you have a combination of
yes.
J1 and J2.
Yes, exactly. Exactly. You can see it more or less from here as well, because the only poles that appear are either in 0 or infinity, so you have two forms. If you would have another pole, then you would have another integral, but in this case, okay, now this analysis was for epsilon equal to 0. Let's put epsilon back. And this is easy in this case. You can show, you can, in particular from this parametric representation, the dependence on epsilon really comes factored out. And so then if now you expand this in epsilon, this will just contribute again with logarithms. And so this won't spoil the property of logarithmic singularity that you wanted to have. And so then we still, even if we put back epsilon, we still have logarithmic singularity. And moreover, then you can check that they satisfy epsilon factorized differential equation, that the entries have only simple poles, indeed they are only d logs, and that the differential forms are independent. And so then you get this nice path order exponential forms, and you get your multiple polylogarithms. So this is then an example on how you get multiple polylogarithms. Okay, so then it's time to put the mass different from 0. Now we cannot do much. The roots don't collide anymore, and we really have a square root. The fact that then an elliptic curve. The fact that we have this elliptic curve, then it means that we have two branch cuts and two independent cycles already just coming from the elliptic curve. But we can try to do the same analysis. So again, if you put nu 5 equal to 0, here we get something like this. So still the d log and then dx over y. But then for those of you familiar with elliptic curves, you can see that this is it's what's called first kind integral. And if you can, one of these two cycles will be such that this integral is holomorphic. And it's an holomorphic period of the elliptic curve. Around the other cycle, it will behave like a logarithm. And so then this not that different with respect to the square root that we saw before. So we can simply divide out. And so then we still have the nice properties that we wanted. So the logarithmic structure. You can do the same for u5 equals to -1. And again, you will get a pole at infinity. And you can, again, integrate. And this time here, it's what's called the third kind integral in the context of the elliptic curve. And in this contour, it will just give you something proportional to 1, so it's even simpler. This is already a good candidate. Now, the thing that goes wrong here is that, unfortunately, mu5 equals to -2 is not dependent anymore. And you will get then, the integral will look like this. And this is now what is called the second kind integral. And this is not independent. Also, you know it from the theory of elliptic curves that you have at least a basis of 2 differential forms. But moreover, this is not really the problem. The problem is that this has a double polar infinity. And so then it looks like we don't have any logarithmic singularity. So it looks really that from this elliptic point of view, we cannot get what we wanted to get at the beginning. Also, okay, you can rewrite it in a way such that you remove a contribution from the simple pole. So this is the true second kind integral that has a double pole without residue. But then if you try now to integrate this multiple times, you will get that this rational function, like coming from 1 over x squared, will mix with logarithms. Because now you have to integrate the 1 over x squared that will give you 1 over x times some function. If you do it again, you will get both logarithms and the rational function. And so you really don't see the logarithmic property here. Moreover, if you try to put back epsilon, for the first 2 integrals, there is no problem. It behaves the same way. But for this one, there is. Because now, since you have to integrate this, the integration will also act on the epsilon part. And so you will already not get not only log contribution, but you will also mix epsilon. So you will really get a mixture of things coming from this integral. And so then the first question that you can ask ourselves is that it, or we can find a better differential form? And maybe for this, we can look at the middle homology. In particular, in our example, the middle homology of the elliptic curve. So this is the non-vanishing, part of the middle homology, complexified, that can be written as a direct sum of h10 and h01. And maybe if you're not familiar with elliptic curves, you have to again believe me. Here, this part is spanned by the differential of the first kind, while this one is spanned by the differential of the second kind. However, we can also find a different basis through Griffith transversality. This means that we can still pick the unique holomorphic one form to span the first part, but we can also take the derivative with respect to an external parameter of this form, and this will be in the direct sum of both the spaces. So then it means that this will be a candidate that can also span our second differential form. So what I'm saying is not necessarily you need to have a second kind differential, but you can also use the derivative of a first kind to span your space. Why I'm saying this? Because you can imagine that you found a canonical integral, where here, for example, these are purely logs, and these are coefficients such that your transcendental weight is the correct one. So this behaves like log 1, this behaves like log to the power of 2. If you now take a derivative of this, you see that it's not that bad. You will get some algebraic function coming from the argument of the log. But then still, if you divide by epsilon, here you see that this has transcendental weight 0, this is transcendental weight 1. So at least you have a good property. It's not pure anymore because we have this algebraic object, but at least it has the good transcendental weight. So then it looks like taking a derivative is a bit better choice. But then the question is, how do we remove this algebraic contribution? And for this, I will I will do a step back and talk about the second flavor that I wanted to tell you today, that is intersection theory. So in terms of Feynman integral, intersection theory has been introduced in these 2 papers, more or less. And this comes from the fact that, as I already showed you, you can write your integral in terms of this parametric representation. So this was the Bikov polynomial that we saw before. It's not important the shape. The important is the power here. And what is the topic of intersection theory? Well, the thing is that, as you see here, already just looking at the 2 epsilon, you know that Feynman integrals are multi-valued, because here now epsilon is real, so this power is not integer, and so then you can have monodromies around the singularities. And so then the appropriate framework to talk about this is indeed twisted cohomology, where the twisted cohomology deals with integral of this form, where this is a multi-valued function that in our case is our Bikov polynomial. These are rational differential form, and now we will restrict to the maximal cut, so we will put all of this, we will compute a residue over all of this. We don't want to consider also the singularity, but this is just a technicality. But so this basically are our differential forms, and this is our integration contour. And so then we can define a twisted cohomology group that is the space of closed differentials up to total derivative. And the important, okay, this is just the space, usually it's just Cn minus the singularities. The important, okay, and this is the derivative that you have to act on the differentials. But I don't want you to remember all of this. The only thing that I want you to remember is that now a basis of these forms, it's more or less equivalent to a basis of the master integrand. So you can see here, these are like, this correspond like to the different differential forms that you can have to span your space of master integrals. And then on the other hand, you can define a twisted homology group where there is a space of these integration cycles. So, and again, okay, this comes with a choice because then they are multi-valued. But okay, the important thing is that these forms here really behave like our basis of master integrals. Why am I saying all of this? Because then I just wanted to tell you that this is the natural language for talking about Feynman integrals, since they are intrinsically multi-valued. But I don't need much from the framework of twisted cohomology from this talk now. What I need is just to define some pairings. Okay, let's start from our cohomology space and homology. You can, they come with dual groups, but again, I don't want to really define this dual group. I want just to say that Poincare duality tells us that there is a dual homology group and also a dual cohomology group. And they are important because then they let us define the pairing. Okay, this pairing, it's not doesn't depend on the dual, but I still wanted to introduce here. And this pairing, so it pairs a differential form with the twisted cycle. And what is this? This is just our integral. Okay, so these are our basis integrands, and these are our basis cycles. And then we also have this other pairing that I want to use today, called cohomology intersection pairing, that pairs the form in the cohomology and the forms in the dual cohomology. And a priori, it is that it's rational both in the kinematic and in epsilon. You can define either pairings, homology and the dual period pairing, but they are not relevant for today, and they are also related. But okay, the one that I want you to remember are these two, where this is basically the integral, and this is the pairing of the two of the forms. Why I want you to remember to these two? Because if you look at our differential equation, what this is actually saying is that the same differential equation matrix will be the one when we consider the full period matrix, because the full period matrix is just exactly the basis integrand, but maybe evaluated at different cycles. So then this differential equation has to be the same for our integrals and for our period matrix. And so what I wanted to maybe say from this is that this is the important object that we want to look at if we want to find a solution. So if we want to find a solution of this differential equation, we really need to look at the period matrix differential equation. Yes.
What are these two dual?
Yes. So these are the dual cohomology. Okay. They are, for example, this one is the dual cohomology, and to have it defined, you need the space of compact forms, because these
with compact support.
exactly forms with compact support. exactly. While this one is the locally finite homology. So here you need the locally finite cycles, because instead here in the homology that we are using, they are regularized cycles. So if you have something that diverges here, then you have something that is finite here, and vice versa. They are defined in this way because then in this way the pairing makes sense, because these forms have any support, it's not compact necessarily, and so then to have this pairing well defined here, you need something that has a compact support. Yes.
So these are forms that have zeros where those have singularities.
Yeah, I think they are, you like remove the part from where these are singularities and you put something from the bar, so from the complex conjugate part. So yeah, I think, yes.
Compact support cannot be analytic at all. So
Yeah, it's it has some holes. Yes, exactly. So
you are pairing analytic functions.
no, wait, sorry. This is not holomorphic. Yes, that's an anti-holomorphic component. Yeah, indeed, this product makes sense only if you here you have some anti-holomorphic part, because otherwise it will always vanish.
And the n is not n comma 0, just to note. N is k plus n. I mean,
n is it's just like that. Yes, then this you can split into 1 comma n plus 1, n minus 1, then 2 comma n minus 2.
all of them.
Yes, now I don't know if all of them are not vanishing, but in twisted cohomology, only the middle dimensional cohomology doesn't vanish. So like this is the same space. So n is the same as the dimension of x. All the others vanish. Okay, and so then this I am telling you because now we can go back to our sunrise example and write the period matrix for our sunrise example. This is the first integral to the holomorphic form, and this is the logarithmic form, and this is the derivative. So we chose a derivative basis. And now you can actually show that you can split this matrix into two parts, where the first part, this is just an algebraic, this is the determinant of the matrix that is algebraic. The first part contains all the algebraic part, all the algebraic elements, while the second part contains the logarithms. I told you before that psi1 behaves like a log, and so indeed, this one really contains all the logarithmic singularity of our integrals, while this contains the algebraic part. And you can do this for any geometry. And the only thing that I want you to get from this is then we found a way to generalize what we wanted to get. So since this is the algebraic part, we can just multiply our integrals by it. And so then in this way, our integrals will behave just something like logarithms. Okay, we need to do like, as I showed you before, we have to multiply by epsilon to the minus 1 to get the correct weight. But okay, this is just a multiplication. And however, this is not enough, because sometimes if you get this logarithmic part, still here we're working for epsilon equal to 0. But if you also want epsilon factorization, we might need to add another rotation and to bring this into this form. And now this rotation is just defined by some functions that are fixed by requiring that all the powers that are not proportional to epsilon vanish. Okay, but then if we do that, we do get indeed epsilon factorized differential equation. The entries will only have simple poles, but now it's a local concept because we don't have logarithms anymore. We only have logarithms close to singularity. So we will not get like a d-log differential equation object, but we will get something that behaves like a simple pole. And then the differential form will be independent. So we actually managed to find a way to, again, get what we wanted to get in the polylogarithmic case. Okay, you can check. If you do the limit for the capital M to 0, you will get the same thing as before. Okay, now let's take maybe a step back and wait, I am over time, right? Okay, no? All right, it's 11:30%. Okay, so let's take a step back and let's relook at what we did. So what function did we introduce in the canonical differential equation? So the first rotation that we put was this to eliminate all the algebraic objects. In our case, it contained the transcendental object. And then we had to introduce these functions to epsilon factorize. And in the case of the sunrise, the matrix that you introduce looks like this, where you keep this one not determined, and then you fix them by requiring that all the terms non-proportional to epsilon vanish. So then a priori this function can be everything, and but they are defined by the first order differential equation because they are defined such that the non-proportional to epsilon terms will vanish. And so then if you want to solve them, there will be some integrals of the elements that already appeared in the differential equation. So they will contain these objects. And so in our sunrise case, they will look like this. And so then one question that you can for sure then solve them by series expansion, because then you can expand your period, you can expand the rational function, and you can get an expansion of the solution. But then still you might want to ask, what do they evaluate to? Like, are they really new objects, or you can write them in terms of other transcendental function? And intersection theory will tell us something about it. And also, I have presented you these three steps or three requirements, but you might wonder, like, are these really all different, or can they be equivalent? And it has been shown that they are not equivalent. In particular, they found an epsilon factorized differential equation that didn't have independent form. And so then another question is, can we really distinguish between something that is canonical and something that is not? And again, intersection theory will tell us something about it. And so maybe this is the last concept that I want to tell you about today. So this is where now we use the intersection matrix that I introduced before. And I told you that a priori this can depend on the kinematic and also on epsilons. Now, you can also rotate this object to the canonical form, so using the same rotation that we found before. And if you do that, you actually discover that it doesn't depend on the kinematic anymore. So if you take a derivative with respect to the external kinematics, you get 0. And so then it's a function that depends just in epsilon times a constant matrix. This might be not too, I mean, this is really, I find really surprising, because at the beginning could be anything, but now in this particular basis is constant. And this is not just nice, but it can also help us, because what do we put in the intersection matrix when we rotate to the canonical form? Well, we put all these transcendental objects, these functions that a priori are unknown, and they are all there. But if we know that our canonical intersection matrix has to be constant, then it means that these new functions cannot be fully independent. They have to be related, because if they appear in this delta, but in the end we know that delta is constant, then it means that there is some relation hidden in these functions. And okay, we have found in particularly that you can write your last rotation, the one containing this unknown function, in terms of a matrix called O and a matrix called R. And in particular, you can show that R fully depends on the transcendental object that you already put. And so then we found a way to reduce the number of this new object. And I just wanted to show an example. You can do the next step. Instead of considering the sunrise, you consider the three-loop banana integral.
Can you ask about the previous
Yes.
slide? So this property that is constant, what is the reason?
It really comes from the linear independence of the forms. So if you didn't have forms that are independent, you could not have got it. That's why we really need it to be canonical and not just epsilon factorized.
So I should think of it as some sort of Wronskian or something like that.
Wronskian in what sense?
Okay, maybe we can discuss
Yes, perfect. So then if you look at this integral, you can do the same analysis that we did before. I will not do it. And you will get that instead of an elliptic curve, we will get an Hewlett variable for parameters K3 variety. And so then it means that when you want to find your canonical differential equation, you will have to input the information coming from the periods of this K3 variety, and also these new functions. And in this case, they are 23. So like it's a lot of them. And so then it's really a problem that has a high complexity. But it turns out that if you use these tools from intersection theory, in the end, this 23 function boils down to 2 integrals. So it really simplifies a lot the functions that appear. Okay, and then so this brings me to my conclusion. I hope if you didn't know anything about the canonical differential equation, now I managed to tell you why it's important, because it both can help us in finding a solution for the Feynman integrals. And I hope I also managed to show you that different geometry in the end can have similar properties. And then the second flavor that I maybe touched a bit less was the twisted cohomology. And it's again, I wanted to show you why is the natural framework for Feynman integrals. And it's not just a natural framework, but it can actually be used to simplify calculations. Now, these methods, both only this one and both applied together, have been quite successful so far. So they have been applied to a variety of cases, also in gravitational waves. While twisted cohomology, as I said, it has been introduced relatively recently. And in particular, this has been introduced in the context of finding a good a starting basis of your integrals. While the way we use now, it was to connect to the canonical differential equation, so to get some maybe to use as a tool for simplified calculation. And we're also working on using it to find some symmetries. So with these 2 points, I wanted to say that it has a variety of applications, the twisted cohomology framework, not just in the context of amplitude for QFT, but also in the context of string amplitudes and the cosmological correlator. So it really seems to be a good framework. Of course, there are still maybe some questions. So can we understand better this function that we have to introduce at the end? And now I didn't tell you about what goes beyond the elliptic curves. But then when you go beyond the elliptic curve, maybe the cohomology is not enough. You need to look at the mixed structure of the underlying variety. And so then can we understand better the relation between mixed structure and Feynman integral and how to actually get the mixed structure from it? And then, okay, our method is not the only one. So this way of finding a canonical DQ is not the only one. So it would be nice to have a better comparison. And of course, I mean, in the end, we want numbers. And so then it would be important to see how well it behaves with a numerical evaluation. And so with this, I thank you for your attention.
Thank you, Sara. Any question or comment?
In the case of the 4 masses,
Yes.
can I, at which level, from Markov or whatever, can I see that I have a K3 with 4 parameters, and how do I get the Fuchs equations for this? Just looking at this, so when do I get it? Okay.
Maybe just looking at this, you don't see it immediately, but you can do exactly what we did before with the sunrise.
Yes.
So if you cut all your propagators, in the end, instead of having something like dx over a square root of 4 degree 4 polynomial, you will get exactly the Euler-Verrill equation, polynomial equation. So maybe I can also.
How does it look? Euler-Verrill?
It's I mean, okay, if you don't homogenize your parameters, you will not get it immediately. But if you do homogenization, then you exactly get the same polynomial equation. So what was it, degree 4?
It's a quartic into variable.
Quartic into variable, yes. So you will get exactly the same polynomial that defines it.
Mm-hmm.
I can also show you later. Now I don't have it on the slides, but you exactly get.
And this K3 is not the special K3 that gave bilinears in elliptic in E's and K's, because there was the K3 which was the Adamar product of elliptic curves.
But I think that was for only one variable case. I think that was for equal mass.
Yes.
And then in the equal mass, the geometry becomes more singular. And so then it actually gives you a product of elliptics.
But it's not the case.
No, if you here have all the 4 different masses, then no. But otherwise, if you put all the masses to same value, then you will see the 2 elliptic curves. Yes. Actually, also not only that. Okay, I have too many animations. But, also, if you put one mass M1, and so if you put this M1 and this 3, you put M2, you still will find the product of two elliptic curves that now depends on tau1 and tau2. So you will get the yes.
What kind of cohomology is your twisted cohomology? Can you show again? Is it something like cohomology of a connection with regular singularity or something like?
Yes. So here I am in the framework of non-relative twisted cohomology, because if I compute the maximal cut, then all these poles will go away, and so I only have the poles of the twist. And so in that sense, then it's a twisted cohomology. While if I don't look at the maximal cut, but I leave this, then I am in non-relative twisted cohomology, because then these poles are not regularized by the twist.
So can you show the definition of a twisted cohomology?
Yes. So it's just the external derivative plus d log of the twist.
Okay, and then you take a cohomology on some space, which is
Exactly.
geometrically, it's non-compact or
Compact.
it's compact?
Yes.
It's compact, but the connection is some pole has some singularity.
Yes.
And then in this case, there are different cohomologies you can take, like.
Yes.
Is it like
Indeed. Here I am taking the DRAM.
the RAM? Okay.
Yeah, I didn't. It's isomorphic to the DRAM, but yes, I am taking
Okay,
the DRAM.
the RAM is.
Exactly. Maybe it's better to see it from here. So then this is the DRAM, and then it's dual to the compact, and the forms with a compact support.
Okay, so the RAM on the non-compact open the
Yes.
right.
No, I'm not. I
So
think
there are several cohomologies, like in the non-compact case, you have cohomologies, it's compact support also, the intersection cohomology, and then you can have coefficients in some D-module or let's say connection possible with regular singularity, you do such things also, but I'm not sure what your.
so. Wait, my space is always this one. So it's Cn minus the singularity.
Okay. Okay, so you consider. Okay, so this makes sense. You take algebraic DRAM cohomology of basis coefficients. Okay. Okay.
Yeah, and then if you want to find the pairing correctly, then here since these are regularized cycles, here you need the locally finite ones, and to make sense, because these cycles will be something like, if you have here two singularities, the cycle connecting them will go like this, and then have a ball of radius epsilon, and the same on the other singularities. And while these one are the finite ones, so these are the locally finite ones.
So you have cycles with coefficients and local systems.
Yes. So yes, they both have coefficients in the local in some local system. So they come with a specific choice of the branch point of psi. So yes, so the cycle is coefficient in the local system. So then for each cycle, you need a specific choice of your branch of the psi.
Thank you for the nice talk. I have made one, maybe two questions. The first one is about the dimension. We are focused in the dimension to right, in the first part of your talk.
Yeah.
We are b equal to 2.
Yes.
That's the reason why you get an elliptic.
Yes.
And what happens for different dimensions if I choose, for example,
so as far as I know, most of the odd dimension, if you choose an odd dimension, then you will get something simpler always. But the thing is that the odd dimension doesn't connect to 4. So if you want your Feynman integrals in the end to live in 4 dimension, then you need to start from an even dimension.
Yes.
So I think in d equals 3 here, it's even the elliptic one will be a polylogarithmic one. I think. I'm not sure.
It is the fact that you find an elliptic curve is depend by the choice of the dimension, because you are in dimension 2, but if you start from another integral with a different dimension, you don't see this geometry. Proper of the dimension.
Yes, you maybe don't see it direct because no. Yes. Because here if we put a 2, then it's a 4 minus 2.
You put a 2, yes.
Yeah. No, if
Yeah.
we don't put a 2, then maybe it's a bit more complicated to see. But since you have always this shift shift relations, any of the even one should be connected to the 2. So I think you don't. Yeah, you will see something different. But maybe the elliptic one is the easiest to deal with, and so then you go to 2 for doing that.
I mean, for example, I have dimension 3.
Okay.
If I have dimension 3, what happens?
Yeah, I think it's a polylog.
But it's worse, no? You have a square root of b instead of you have a half integral power of b instead of integral. Yeah, it looks worse.
But
Yeah, to force.
I think in this B there are already some powers. I think this B maybe contains some power already, and then it simplifies. I think now I'm not 100% sure. Because here, if we put here 2, would be 4 minus 2, 2 divided by 2, 1. But in the end, what we see from here will be a square root. So then, even if this is a 1, in the end here we get a square root. So I think here there is still some.
It's strange. You had an elliptic, it was finally you had square roots. So if you have worse than square
No,
roots.
but B is not a quadratic. B is a quadratic.
Mhm.
That's the difference. So what you get is a square root of a quadratic and then a polar infinity. So you can still compute the residues. So it's after you take the first residue that you get then you see that you have the elliptic curve. So it's hard to see at this stage what happens further down.
Yeah.
And the second question was about the fact that at a certain point you have some simplification because you consider the moon point.
Yes.
You are considered the parameter space of your elliptic curve, right?
Yes.
And why, which is the critical reason?
No, in principle, you can consider all the singularities. The analysis around the Mount point is the maybe simplest because you have all your periods that are independent one another. So you have the holomorphic, then you have the period that behaves like log, and then the one, okay, in the standardized case, you only have 2. But if you go to a K3, then you will have a log squared period. While maybe around other singular point, this will not be the case. So maybe you will have 1 holomorphic and 2 log. And so then maybe there it's a bit, I think, a bit more difficult to see it cleanly. But and so then the analysis, it's nicer there. But then still you can do exactly the same there. And in the end, what you require is you want the holomorphic one. So if you find still an holomorphic, if you find 2, then maybe you will look for a combination such that you will still get simple pool at the end. So maybe you need to do a bit of manipulation on how to get the correct one, but in the end it works also in the other point. And then you can expand around all the singular points to have all the parameter space.
There was a question there.
Yeah, I was a bit confused because when you showed the Roskian for the elliptic trace,
yes,
there's only a log there. I thought like I should see elliptic functions somewhere.
yeah, they were the elliptic function because the psi 0 that I showed there, it's this. So it's exactly the integral over the dx over y.
But when you showed the W matrix,
yes,
you mentioned that one part contains the log, the other part contains the algebraic.
Yes. Okay. Yes. So, but this is the. I said that it's the log when you expand around the mountain. Otherwise, this in general it's the elliptic A, and also this one would be the elliptic A lambda minus 1. So these are the elliptic function. But then if you look around the singular points where you can actually see this logarithmic structure, then in the end this is just a log, but close to the point. Otherwise, it's an elliptic function. Yes. And here I'm doing the analysis close to the point because I wanted to show you how the singularity behaves. Maybe the function is more complicated than a log, but the important thing is that close to the singularity, it behaves like a log.
But it's elliptic integral, right? Not elliptic function. It's like a hypergeometric
function at the end of the day. That's why
Yes.
this local behavior
Yes.
happens. It's not like two periodic functions.
Yeah, no. Mhm.
I think physicists are sometimes political in.
Yeah.
When I heard about
I apologize for all the wrong
Yes.
Yes.
When you showed that the intersection matrix doesn't depend on S.
Yes.
Yeah.
Yeah.
I think previous.
Oh no, I think this one. No?
Here. I missed why also the depends on epsilon factorized.
Yeah, this is, I didn't say indeed, that's a good point. You don't see it directly from here, but you can check that if you put a matrix a matrix, not just a function that depends on epsilon, you can check that it always commutes. And so in the end, you can even check that not only always commutes, but okay, you can check that is proportional to the identity. And so say since it's then proportional to the identity, then it's just a function in the end. But okay, it's not obvious. So you need to show it.
In fact, I'm confused why it depends on epsilon, because I thought that these dual forms you had to flip the sign of the twist.
Yes.
So I thought the twist just disappears.
You have to flip the side of the. That's true, but wait, no, it doesn't disappear for sure. Now I'm thinking, because I think maybe it can't be, because then you have also to find the compact support, and so then maybe in doing that some rational part affects the twist. This I have to recheck, but
I see. Maybe it's because the cohomology itself, the definition has the epsilon.
Yes.
Yeah. Okay. That makes sense.
Yeah, because you still have to use the
covariant derivative.
exactly, and that contains epsilon.
So you always check that the same matrix that brings the equation in canonical form actually diagonalize the appeared matrix. Okay?
Yes.
Yeah.
Yes. I mean,
that was the alpha conjecture. So in the paper you showed before.
Yes. The alpha paper. Yes. Yeah.
Okay. You showed that it actually happens in the case you analyze.
You mean if our canonical form actually has a constant homology? Yes.
Yes. Diagonal appeared matrix. Yes.
Yes.
Any other questions also from Zoom? And if not, we can thank Sara again.